A $70 million fighter sits on the bow of a nuclear-powered aircraft carrier. Behind it, a steam catapult is charged to roughly 90,000 pounds of force, enough to take that aircraft from 0 to 165 miles per hour in under 3 seconds. The catapult is ready. The pilot has the engines at full power, and the aircraft does not move. Not because anything has failed. Not because the brakes are holding it. Because a single steel fitting, roughly the size of a human hand, is holding the entire machine in place. And until that fitting lets go, nothing on that $13 billion ship can make the jet move 1 inch. That is not a malfunction. That is the design. And the reason it works that way is more counterintuitive than it sounds. Here is what makes this strange. A catapult generating 90,000 pounds of force cannot launch a fighter jet without first getting clearance from a piece of steel that costs somewhere around a few $100s. The fitting is not electronic. It receives no signal. It reads no sensor. It simply holds. And then, at a precise threshold of tension, it lets go. That threshold is engineered exactly. If it is off, too early or too late, by even a narrow margin, a $70 million F/-18 Super Hornet either falls short of flying speed off the bow or takes a structural jolt at the wrong moment in the stroke. The full answer to why this works, and why every carrier in the US Navy fleet depends on it daily, takes some unpacking. We are going to go through it layer by layer. And somewhere in the middle, we will get to the part that almost nobody talks about. The economic asymmetry of a fitting worth less than dinner holding back a machine worth more than some countries spend on defense in a year. Stay with this. To understand why the holdback fitting exists at all, you first need to understand what a catapult actually does on a carrier deck, and why launching a jet from a ship is a different engineering problem from launching one from a runway. A land-based aircraft departing from a base in Guam, Japan, or Diego Garcia has thousands of feet of runway to accelerate down. The engines provide the thrust. The aircraft reaches flying speed under its own power. The runway is a passive surface. It does not push. A carrier flight deck on a Nimitz-class ship is roughly 1,000 feet long, and most of that length is occupied by parked aircraft, ordnance, maintenance equipment, and the arresting wire system on the aft end. The usable launch run for a catapult shot is somewhere around 300 feet, less in some configurations. A fully loaded F/-18 Super Hornet, carrying external fuel tanks and a combat weapons loadout, cannot reach flying speed in 300 feet on engine power alone. The physics does not allow it. The catapult fixes that. It delivers a burst of stored energy, a supplemental kick that covers the gap between what the engines can do and what flight physics requires at the end of a 300-foot deck. Steam catapults. Specifically the C-13 type that equips Nimitz-class carriers including USS Carl Vinson, USS Theodore Roosevelt, USS Abraham Lincoln, and the others, work by pressure. Steam is generated by the ship's nuclear reactors, routed into accumulator cylinders beneath the flight deck, and released in a controlled burst through a piston running in a slot that spans the full catapult stroke. The piston connects to a shuttle, a metal sled riding in that slot, and the shuttle is what physically connects to the aircraft at launch. The nose gear of an F/-18 Super Hornet interfaces with the shuttle through a launch bar, a forward-projecting arm on the nose gear strut. When the aircraft taxis into position on the catapult, the launch bar drops into a receiver in the shuttle and locks. The catapult is now mechanically connected to the aircraft. But there is a second attachment point. On the aft face of the nose gear strut, there is a small bracket, the holdback fitting. This connects the nose gear to a fixed deck point behind the shuttle. The holdback is a tension device, designed to resist pulling force up to a calibrated limit and then release when that limit is exceeded cleanly and completely. So the aircraft is connected to two things at once. The shuttle in front, which will pull it forward. The holdback behind, which holds it stationary until the right moment. And here is the problem that setup solves. If you simply charge the catapult and release the steam without a holdback, the shuttle would immediately begin pulling the nose gear forward. Before the pilot had engines at full power, before the catapult had built peak pressure, before any of the system was synchronized, the launch would be uncontrolled, and the energy transfer across the stroke would be wrong from the first instant. The holdback is what allows the catapult to be fully charged, the shuttle to be brought to tension against the aircraft, and all that force to be preloaded, while the aircraft stays stationary. The pilot brings engines to full military power or afterburner. The deck crew confirms systems. The shooter, the officer responsible for the launch, scans the deck. and then the catapult fires. The shuttle drives forward. The tension on the holdback spikes instantly to its rated release load. The fitting lets go. That release, not the catapult firing, not the engine thrust, is the moment the launch actually begins. The aircraft starts moving with the catapult already at full stroke pressure and the engines already at maximum thrust. Everything is synchronized by the physics of that one fitting letting go at the right instant. Here is where the complication lives. The holdback fitting is not a universal part. It is rated, calibrated to a specific release tension, and that rating has to match the weight and configuration of the aircraft being launched. A Super Hornet configured heavy, with external tanks and a full strike loadout, weighs significantly more than the same aircraft clean, or a lighter type like an E-2D Advanced Hawkeye. The catapult steam pressure is set per launch to match the aircraft weight. The holdback fitting rating has to match both. Use a fitting rated too low, and it releases before the catapult reaches full stroke pressure. The aircraft starts moving early, before the full energy is available. By the end of the deck, it is short of flying speed. The difference between flying and not flying at the end of a carrier deck is not a matter of a few knots. It is a binary outcome. The aircraft either has enough energy or it does not. Use a fitting rated too high, and it holds past the point where the catapult stroke is fully running. The aircraft resists a moving shuttle. The nose gear absorbs force. It was not designed to take that way. And when the fitting finally releases, the transition is abrupt rather than smooth. Neither outcome is acceptable on a flight deck running dozens of launches per day. The window between too early and too late is not generous. Every launch requires a fitting with the correct rating, correctly installed and verified, for that specific aircraft at that specific configuration. In earlier generations of carrier catapult systems, the holdback solution was a breakaway fitting, a small steel bar machined to a specific cross-section that would physically fracture at a calibrated tension. Install it, charge the catapult, bar breaks, aircraft launches. The broken fitting gets swept off the deck. One launch, one fitting. Every time. The economics are worth laying out. A breakaway fitting costs somewhere in the low hundreds of dollars per unit, on a carrier running at surge tempo, up to around 120 total sorties per day during peak operations. The fixed-wing catapult launches might consume 50 to 60 fittings in a day. At $300 each, that is roughly $15,000 to $18,000 per day in consumable fittings. Against the daily operating cost of a carrier strike group running into the millions, the fitting cost is essentially invisible in the budget. What is not invisible is the inventory. The fitting has to be the right rated part for the right aircraft at the right configuration. On a carrier air wing that includes F/A-18E and F/A-18F Super Hornets in multiple loadout configurations, EA-18G Growler electronic warfare aircraft, E-2D Advanced Hawkeye command and control aircraft, and C-2A Greyhound logistics transports, the variety of required fitting ratings is significant. What's most surprising about managing this system isn't the cost per fitting. It's the inventory discipline required to run it correctly at operational tempo, at sea, with no parts warehouse within reach. Each launch requires someone to pull the correct fitting from inventory, install it, and confirm the rating against that aircraft's posted weight. Do that wrong once, and the consequence is not a broken part. It is a $70 million aircraft in the water and a pilot in the ejection seat. The repeatable holdback bar, sometimes called a repeatable holdback device, depending on implementation, takes a different approach. Instead of a bar that fractures, it uses a mechanism designed to release at a calibrated tension, be recovered, inspected, and reset for the next cycle. The supply chain advantage is straightforward. No consumable stream of breakaway bars, no constant inventory sorting by rating, no deck sweeping of broken steel after every shot. The fitting releases, the aircraft launches, the fitting is recovered and goes back into rotation. But the repeatable mechanism introduces its own failure modes. A breakaway bar fails in exactly one way. It breaks. The failure is instant, visible, unambiguous. A repeatable release mechanism can fail more subtly. Release thresholds can drift as components wear across hundreds of cycles. A mechanism can release correctly most of the time and then, on a specific launch cycle, under specific conditions, hold slightly longer or release slightly earlier. The repeatability is only as good as the manufacturing tolerance and the inspection regimen sustaining it. Here is the take that will probably generate some disagreement. The breakaway fitting is arguably the more predictable system, not because it is more sophisticated, but precisely because it is less so. A bar machined to a calibrated cross-section has no moving parts to wear, no mechanism to drift over time, and no ambiguity in its failure mode. The supply chain cost is real, but the failure mode is constrained and visible in a way that a reusable mechanical release is not. The U.S. Navy has invested in repeatable holdback technology because the supply chain problem at high launch tempo is a genuine operational constraint. But both approaches carry trade-offs. They just take different shapes. Here is where the loop closes, or rather, where it opens one more layer deeper. We said at the start that the holdback fitting, not the catapult, determines whether the launch succeeds. Let us be precise about why that is true. The catapult delivers a fixed energy envelope for a given steam pressure and stroke length. That envelope is set before the shot. The catapult does not respond in real time to what the aircraft is doing during the stroke. It applies force, and the aircraft either tracks that energy curve or it does not. The catapult is the supply side of the equation. The holdback fitting is the timing gate. It determines when the aircraft begins moving relative to the catapult's stroke. Start on time. At the exact moment the shuttle is at full tension, and the aircraft tracks the energy curve correctly through the full stroke and exits at design speed. Start too early or too late, and it does not. This is why the holdback rating tolerance is expressed in a relatively narrow band of force. The aircraft weight has to be posted accurately. The fitting rating has to match. The catapult pressure has to be set correctly for that weight. 3 variables, all with tolerances, all of which have to land in range simultaneously for every single launch. On USS Gerald Ford, the lead ship of the Ford class and the first U.S. carrier to commission since USS George H.W. Bush in 2009, the catapult system is EMALS, the electromagnetic launch system, developed by General Atomics rather than the C-13 steam type on Nimitz-class carriers. EMALS drives the launch carriage with a linear induction motor rather than a steam piston. The control system is substantially more capable. It can shape the force profile across the stroke, starting lower and ramping to peak, rather than delivering a fixed steam pressure curve from the first instant. The implication for the holdback is meaningful. Because EMALS can modulate its force delivery, the interface with the holdback release mechanism can be tighter. The energy ramp-up begins slightly before the holdback releases, and the transition from stationary to moving is smoother than a steam catapult's comparatively sharp impulse. On paper, this is a real improvement. EMALS is gentler on airframes. The shaped force curve reduces peak stress on the nose gear and forward fuselage structure compared to the steam catapult's impulse. Over hundreds or thousands of launches per deployment year, reduced peak stress per shot translates directly to extended airframe service life and lower depot maintenance cost. The caveat is the reliability record. Early operational experience with EMALS on USS Gerald Ford produced mean time between failures significantly worse than the Navy's threshold requirements. The system required substantial modification after commissioning and delayed the Ford's operational capability. General Atomics and the Navy worked through multiple software and hardware revisions before the system reached acceptable performance levels. The Nimitz-class steam catapult, with decades of operational history behind it, had no equivalent early life reliability gap. What that tells us about the broader engineering challenge is this: the catapult and holdback system, steam or electromagnetic, operates at the intersection of extreme force, precise timing, and very high operational tempo. The margin for error is narrow. The consequence of error is immediate. The system has to be operated reliably by a flight deck crew working in one of the highest noise, highest tempo environments in any military service. 24 hours a day, at sea, in any weather the Western Pacific delivers. The economic geometry here is worth stating precisely because it is one of the starker examples of cost asymmetry in military aviation. A breakaway holdback fitting costs somewhere in the range of $200 to $400. An F/A-18E or F/A-18F Super Hornet, the primary strike aircraft on most U.S. carrier air wings today, carries a unit flyaway cost of approximately $70 million. The ratio is roughly 230,000 to 1. The part that must function correctly for the aircraft to launch costs less than a single day of flight crew per diem. Extend that across the fleet. The U.S. Navy operates 11 carrier strike groups centered on nuclear-powered carriers: Nimitz-class ships, USS Nimitz, USS Dwight D. Eisenhower, USS Carl Vinson, USS Theodore Roosevelt, USS Abraham Lincoln, USS Harry S. Truman, USS Ronald Reagan, USS George Washington, USS John C. Stennis, USS Harry S. Truman are the backbone of that force. USS Gerald R. Ford is the first of its class, with USS John F. Kennedy commissioned in 2024 and additional hulls under construction. Each carrier air wing carries roughly 60 to 65 aircraft. The strike component typically includes 2 or 3 squadrons of F/A-18 Super Hornets, 1 electronic attack squadron of EA, 1 8G Growlers, 1 early warning squadron of E-2D Advanced Hawkeyes, and logistics and rotary wing elements. On a surge day running 120 total sorties, the fixed-wing catapult launches might consume 50 to 60 fittings, a daily consumable cost that barely registers against the strike group's operating budget but represents an inventory management challenge more operationally sensitive than the cost figures suggest. Put yourself in the position of the Air Wing's equipment officer for a moment. You are at sea in the Western Pacific. You have an operational tasking that requires 4 Super Hornets in strike configuration to launch within 2 hours, and your holdback fitting inventory for that specific weight rating shows 3 units remaining. That 4th aircraft sits on the deck, a gap in the strike package, degraded by a $300 part. The strategic context around all of this is not abstract. U.S. Navy carrier strike groups operating in the Western Pacific, cycling through the South China Sea, conducting freedom of navigation operations, exercising with allies including Japan, South Korea, Australia, and the Philippines, maintain a launch cadence that adversary planners watch directly. The ability to generate sorties, to put armed aircraft in the air repeatedly and reliably from a carrier deck, day after day, is one of the primary metrics that matters to anyone planning against U.S. naval power. China's naval expansion over the past 15 years has produced a People's Liberation Army Navy with a growing surface fleet, anti-ship ballistic missiles including the DF-21D and DF-26, and its own carrier program. The Type 003 carrier Fujian, commissioned in 2024, is Beijing's first carrier equipped with an electromagnetic catapult system, a direct technological parallel to what EMALS represents on USS Gerald R. Ford. That is not coincidence. Chinese naval engineers studied the U.S. carrier launch system and invested in the same transition, from ski jump to catapult, for the same performance reasons. The plan's ability to generate carrier strike sorties remains substantially below U.S. Navy capacity. Fewer hulls, shorter operational history, less accumulated experience in sustained at-sea operations. But the direction is clearly toward narrowing that gap through the 2030s. Planners at 7th Fleet headquarters in Yokosuka do not assess Chinese carrier aviation as a current peer threat, but do factor it as a rising variable in the 2035 operational environment. In that context, the reliability of every component in the U.S. launch system, including a steel holdback fitting that costs a few $100s, carries operational weight that exceeds its price by many orders of magnitude. One detail that kept coming up when working through the technical literature on carrier launch systems. The specification tolerance for holdback release tension is a relatively narrow band expressed in pounds of force. And that band has to be hit, every launch, by a part that is selected, installed, and verified by human beings on a moving flight deck in a noise environment that requires hand signals because verbal communication is essentially impossible. The margin is not large. There is a second economic layer here that extends beyond the fittings themselves, and it runs into the billions when you follow it to the end. The F/A-18 Super Hornet has a designed service life of 6,000 flight hours. Each catapult launch imposes a structural load on the airframe, on the nose gear, the launch bar, and the forward fuselage. That is greatest at the moment of holdback release, when the aircraft transitions from stationary to full-speed acceleration in a fraction of a second. The peak load at that instant is the highest structural event in a typical carrier launch cycle. The difference in peak load between a clean, on-timing release and an off-timing release accumulates across hundreds of catapult launches over an aircraft's service life. EMALS' ability to shape the force curve, to ramp up rather than spike, reduces that peak load per shot. If EMALS reduces peak nose gear stress by 30% per launch, and a Super Hornet logs 500 catapult launches over its service life, the cumulative effect on airframe wear is substantial enough to extend maintenance intervals and potentially total service life. The cost of deferred replacement across a fleet of hundreds of Super Hornets, measured in extended service life and delayed procurement, runs into the billions of dollars. A technology investment in a smoother catapult stroke, justified partly by how it interfaces with the holdback release profile, ends up with an economic return many times larger than the catapult program's own price tag. That is the kind of second-order arithmetic that does not appear in a single-frame cost comparison but shows up over decades in depot maintenance schedules and fleet replacement planning. Let us close the loop we opened at the start. The question was, why does a catapult capable of 90,000 pounds of force wait for permission from a palm-sized steel bar? Why does the moment of that bar's release, rather than the raw catapult power, determine whether the aircraft flies? The answer is timing. The catapult is an energy delivery system. It delivers a fixed quantity of energy over a fixed stroke. The aircraft has to begin moving from the very start of that stroke, synchronized with the energy curve, to exit at the correct speed. Start too late. Holdback holds past the moment the catapult is fully engaged, and the aircraft misses the front of the energy curve and exits short of flying speed. Start too early. Holdback releases before the catapult reaches full pull, and the same result from the opposite direction. The holdback fitting is a precision timing gate. It is calibrated to release at exactly the tension point where the catapult's pull on the shuttle matches the system's designed energy transfer profile. At that moment, and only at that moment, is the aircraft in the correct position relative to the energy curve to complete the stroke at the right exit speed. The fact that this timing gate is a steel part costing a few $100s is not a limitation of the engineering. It is the engineering. The forces involved are so large, and the timing window so narrow, that the most reliable mechanism for hitting it consistently, across dozens of launches per day, in all sea states, maintained by a flight deck crew working in extreme conditions, is a calibrated mechanical threshold, not an active electronic control, not a sensor-driven release. A part that holds and then, at a very specific force, lets go. Here is the part that does not sit entirely neatly, even knowing how well the system works. The entire launch sequence of an aircraft costing $70 million from a ship costing $13 billion, crewed by thousands of sailors, operating in a strategic environment where every sortie carries weight in the broader competition in the Western Pacific. All of it hinges on a mechanical fitting a sailor can hold in one hand. The fitting works. The launch record of U.S. carrier aviation is proof of that. Tens of thousands of successful catapult shots from Nimitz-class carriers across decades of operations in conditions from calm to storm. The reliability, in practice, is extremely high, but the margin when it does not work is exactly zero. There is no partial credit for a launch that goes slightly wrong at the holdback release point. The aircraft either exits the stroke with sufficient energy to fly, or it does not. Here is the genuine question this engineering raises, and it is not a rhetorical one. The Navy faces a real choice in how it manages this system going forward. The breakaway fitting, the disposable bar that fractures at calibrated tension, is mechanically simple, unambiguous in its failure mode, and has no wear characteristic to track. It holds or it breaks. The failure is instant and obvious. The cost is the supply chain. Right part, right rating, right inventory, managed at sea, at tempo. The repeatable holdback bar removes the supply chain problem, but introduces a wear and inspection problem. The release threshold can drift over time. The failure mode is subtler. The logistical savings are real, but so is the added complexity of maintaining a mechanism that must perform to tolerance across hundreds of cycles per deployment. And that has more ways to degrade quietly than a bar that simply fractures. Both carry a price in tempo and logistics. Both have a track record. Neither is obviously the right answer for every scenario on every ship class. Which approach actually buys more reliability at scale, running at operational tempo in the Western Pacific? The math is not obvious. Drop your reasoning in the comments. We read them, and the next time we go into carrier air operations, we are going to go deeper into exactly this trade-off. If you want to understand how the recovery side of that same launch cycle works, the arresting wire, the tailhook, the physics of stopping a 50,000-pound aircraft in under 350 feet. That breakdown is next.